Hi everyone, welcome back. Again, thanks for all the wonderful comments I'm getting from people and the encouragement. One thing I could use is more view hours. If I could find 60 people, I know I've got some people following me, who will play this video all the way through, it will give me a fair few view hours and that would be really helpful. Now, this topic is not for those students who are in year 7 to 10, unless they really want a challenge. It's really for those students who are at a high level maths in grade 12, class 12. We call it year 12 here in Australia, and also for a lot of students at university. It's a very specialised technique in solving trig equations. I think there'd be a lot of students out there who'd like to watch this and see what they could understand and where it goes to. Now, if you want to, you can go to the end and I will add to it a graphical representation of why my answers are true and a bit more understanding using a graphing program where you can have a look and see what the answers are. So here we go. What we're looking for is where does the graph of 5 cos x plus 12 sine x equals 13. There is so much presumed knowledge in here. Now, by the way, I've got all my numbers I need there, so I don't have to pick up my calculator during the calculation and during the video. So we also are going to use this technique. I call it ABAB. I don't know if there's anyone else on the planet that calls it ABAB. It's talking about if we had the cos of the addition of two angles or the sine of the addition of two angles. You can use that in this question as well. But we're going to use cos. The two angles, the A and the B, I call them A and B, end up being cos, cos, sine, sine. And cos is an addition. Now, hopefully, I presume a lot of people already know that rule. Depends which country you're in and what you're doing. But it's quite a fascinating thing. So if you went, if you picked up your calculator and you went the cos of, I don't know, say 10 plus 40 degrees, and you use that pattern and went the cos of 10 and you did the calculation, you can see that rule's true. I'm not proving it, it's an assumption in this. And we only want the answer between 0 and 360. So you probably realise that most cos and sine graphs go on infinitely, so we have an infinite number of solutions. So that's the background behind the questions. Here we go. There is this technique that someone thought up, probably historically, I don't know who, a long time ago, and they said, right, okay, normally we're talking about trigonometry, we're looking at right angle triangles. Now, I'm not even going to draw this to scale. So you'll look at it, and I do prefer normally to draw it to scale. We want the numbers 5 and 12. Oops, I accidentally wrote there 13 because a Pythagorean triangle for 5 and 12 would be 13. We're wanting to solve this equation for where it equals 3, not where it equals 13. Or we could do it equal 13. So we want the numbers 5 and 12 somehow from a right angle triangle. Now, if I wrote that as 5 and 12 there, this is where I just said I won't draw it to scale, but I do prefer if I draw it to scale. So 12 is a lot longer than 5. I call it the Mr. Bean method. For those who are not used to my teaching, there are so many things I do that are unique to me. If that was a 5, there's no way in the world that could be a 12. So I'm going to draw a shorter 5 here. Let's make that a 5. And I'm going to draw a right angle triangle there. And they go, wait a minute, if that was 5, that would be 5, that would be 10. 12 would be up there somewhere. So a reasonable diagram. I'm not looking for accuracy, but I'm looking for a reasonable diagram. And what we're going to use is the 5 and that 12. So I can get rid of this diagram because that one's a bit better, a bit more realistic. Now, hopefully from Pythagoras, most people realise 5 and 12 just gives you 13. Hopefully you know your Pythagorean triads. We have ones like 3, 4, 5. If we double those, 6, 8, 10. Each of those will form a right angle triangle. 5, 12, 13 forms a right angle triangle. We have a heap of those called Pythagorean triads. Some people call them triples. Oh, there's so much background in this topic. I don't want to go too far. Don't want to make it too long. So if we wanted to get a 5 and a 12, we want to use a 13. So we want that number there to come into our calculations. Now I have this thing here I call equal off times 1. It's something I've invented over time, a lot of years teaching. And when people get stuck on a question where they're solving or a proof that they're trying to do, these techniques will help people with a lot of their decisions. I've found that over time helps a lot of students who get stuck and you go a blank in an assessment that gets them through and gives them a technique to be able to solve a question they had no idea about. So we're looking at this question and we're going, okay, this is talking about fractions, this is talking about factorising. There's a lot of all of that in this, but I'm going to talk out first of all times by 1. If I took this left-hand side and I multiplied it by 13 over 13, what have I done to the question? Have I multiplied the question and changed the question in any shape or form? So should I times the other side by 13 on 13? There may be people there who need to see this. if I times that side by 13 on 13, what's happened to it? I've times 3 by 1, which means it's just 3. So it's made no difference to the question, and I nag and nag and nag it out. We haven't changed the question, we have rearranged the question. Now, over and over in maths, we want to rearrange things. Oh guys, this could be long, but I think it's really important. So we rearranged it by putting those 13 there, that 13 there. Now, if I leave that 13 on the numerator, and I get the 13 on the denominator, and I put it inside, that means I'm going to multiply this by 1/13. So that 13 goes on the denominator there, and it goes on the denominator there. Now hang in there with me. Oh my goodness, when I explain this sort of stuff, sometimes I say to students, well, wish me luck. It's quite complicated in what I'm explaining. I'm looking for better pens. And it can go, looks ridiculous. And people go, what are you doing? Let's watch what happens. Don't forget at the end, I'm going to put the video of how you demonstrate this. Now, below every video, I put a playlist for this topic. I've got a lot of videos on this. I've also got a lot of simpler videos on solving trig equations as well. So I'll put both those playlists below. If this is way too hard for you, go back to the easier playlist and pick the first one, have a look at it, and it goes through the basics. So this is for those at a very competent level and they want to look at and see what's happening. So here we go. We've got this now. Now this is sort of related to what I call ABAB over here. So I've got a cos, I've got a sine, but by the way, this is plus. So I want that to say plus there, or addition, which means this one here becomes a subtraction. Let's have a look what's going on with that. So I'm going to use that technique to apply to this question. Now, by the way, sometimes it's easy if I got rid of that 13, but I'm just going to leave it there for now. Now, most people I've found over the years need to write the cos x first, and then write the 5 on 13 second. And then write the sine x first, and write the 12 on 13 second. Now, this does look like that. Now, I'm going to write this over here. I'm going to write that that's cos A, cos B, plus sine A, sine B. And I can apply that to that question here in the same pattern. Let's have a look what we've got here. This part here has to equal that bit there. So the cos of B has to equal the 5 on 13. Now I've solved that over here. So in other words, you're saying what is the angle that would give us 5 on 13? So that's the inverse cos. And that angle turns out to be 67.4. Now, by the way, some people need to see it, round off to 1 decimal place. Some people need to also see that the sine of B, so the sine of B is 12 on 13. Now let's go back over our triangle here at the moment. So if I call it B, the cos of B is 5 on 13. So the cos of B, if I call that B, is 5 on 13. Now I'm going to make a little bit of a jump. We'll turn that into, I didn't finish that. That B also turns out to be 67.4 degrees, rounded to 1 decimal place. A little bit of inaccuracy with 1 decimal place, could go 2. So this one's going to be the X. Now most people in these questions will talk about the other angle being alpha. Just a common thing used by a lot of people. That means that one would be the X. That one would be the alpha. So we're looking here for the alpha. So when I go back to my diagram over here, there's my alpha. And that's why I wanted the right angle triangle and I wanted the Pythagorean triad, which gave me the 13. So I can turn into a right angle triangle and figure out what's going on here. So now I know, let's go back to the equation. I've got 13 lots of, and I've got cos x, and now I'm going to write the next thing is going to be the cos. So the cos of 67.4 degrees. Then I've got the, what have I got next? Back to here. I'm going from there to there. Let's go that part there. I've got the sine of x. So I'm trying to solve this equation for x. And then I'm going to have the, or it's actually from there, it's related to that, isn't it? It's the sine of 67.4 degrees. Now that has to equal 3. Now here's the nice part. Because of ab, I can turn that back into just a cos. So look up here, I can go my AB, I can turn it into the A minus the B. So let's have a look here, there's the A, there's the B, there's the A, there's the B. I can turn that into the cos of the A minus the B. I almost go to laugh again. And now we've got an equation to solve. Now here's our equation. It is the cos of x minus 67.4 equals 3 on 13. Now, I don't know if you're going to use this technique in other countries. Australia, Western Australia, it's an important one. And you can get this question in our Year 12 highest level, which is called Specialist. Our Year 12 highest level course, getting solutions to these. If you're in New South Wales, it's not called Specialist, it's called Extension 2. I think it also comes in Extension 1, but I have to check the curriculum and see what's going on. So here's our problem. We're solving that equation just there. Now at that point, I wonder how many people out there could turn that into that with a great level of difficulty. So I'm saying now I have what I call, for those who are struggling, the Peekaboo method. So a lot of my students will look at that and go, I don't know what to do. They're talking about now the inverse cos, the angle, when you get the cos will give you 3 on 13. And that angle, which is, well, I could write it this way, couldn't I? I could write it the inverse cos of 3 on 13, and that gives us the 76.7. So in other words, I can write here that x minus 67.4 degrees is 76.7. Now we've got to find the solutions. Not only the solution, that first solution, but we need to find the others. But before I go there, I'm just going to give you one answer. So obviously, an answer to this question would be 76.7 degrees plus the 67.4 degrees. And we end up with my number over here, which is 144.1 degrees. So now we have one solution. In most places, you probably get 3 out of 4, 4 out of 5 marks. But we need the other solution. That's between 0 and 360 degrees. There is another solution. There's an infinite number if we keep going past 360 degrees. Now let's have a look. System I use is, if we had that 0 degrees, we had 90 degrees. I don't know if you see this all that much. I presume every country basically will use a similar system. Between 0 and 90 degrees, all of sine is positive between 0 and 90. Cos is positive between 0 and 90, and tan is positive. And I'll briefly go to a sine graph, and I go, if that was 90 degrees and that was 180 degrees, sine graphs go up and down to 1. So it goes up to there, comes down to there. So sine is positive in the first quadrant and also in the second quadrant. So between 0 and 90, sine is positive. Between 90 and 180, sine is still positive. But the other graphs, cos and tan, are negative. So when you get to the third quadrant, talk about the first quadrant, second quadrant, third quadrant, fourth quadrant, tan is positive, and in the fourth quadrant, cos is positive. So that means that cos in this one is negative, and we can go on and on about it, and tan is negative. Hopefully you already know that, but look at that in other videos if you want to. So we're looking for the answer where cos is a positive answer. Cos is a positive answer. So let's look at the other possible answer. We're trying to find the other answer here. So cos is positive between 270 and 360. So we're looking for another answer between 270 and 360. Now I'm going to get rid of some of this because it just looks what I call cluttered. So if I've got teachers watching this, which I have, my diagram has now become cluttered. So I'm going to unclutter it. And I go, the answer, one answer was 76.7 degrees. But I want the other answer to this back here. Not to this here, to this back here. So we know that one was 76.7. I'll make it look reasonable if that looks like 76.7 degrees. So that's in the first quadrant. We're talking about a cosine. A cosine is positive in the fourth quadrant. So we go down here, 76.7 degrees. And we end up with 360 minus that. And I get this next angle here, which is 283.3. 283.3 degrees. You can see it's a little bit past 270. So my next answer, if I go back to here and I get rid of this, there was more than one answer. The next answer takes place at 283.3 degrees. So what are my two answers now? First answer was 76.7 plus 67.4. We're adding that to it. The other answer is 283.3 plus the 670 67.4. We end up with these two ends that I've got written over here of 144.1 degrees, and the other one is 350.7 degrees. Now the interesting part is, if you put 144.1 back into there, I think I've already mentioned it in the video, it will give you 3, or approximately 3, you just need more decimals. And if you put 350.7 into there, you get that. And oh my goodness. I'm going to say bye for now, thanks for watching, but after this I'll include some graphics, some graphing programs I can show you that they're the two answers. They're the only two answers between 0 and 360. So here's the case that I've just made. Now if I made it wider, because it might make it a little bit more obvious, there's the graph that we're talking about, and we're saying where does that graph equal 3? So where does that graph equal 3? Now you can see the two solutions. Now we're only wanting the solutions between 0 degrees and 360 degrees over here somewhere. So I can click on this first one here and go, there's a solution of about just over 144 degrees, and you might notice mine was 144.1 because we didn't use enough decimal places in the calculation. Now if I go over to this one over here, you can see the other solution, which was 350.7, which we had on our calculations, and you can see how accurate it is. So the incredible part is you can just look at that and go, I could just use a graphing calculator or whatever I've got and find the answers really quickly. But they're looking for people understanding the techniques that you can use, especially when it gets to higher level maths. Well, I could probably say again, thanks for watching, bye for now.